We shall now look at the energy stored in stretched or compressed springs. If we apply a force on a spring to cause it to move or extend, stretch in other words, by a particular distance d, then we know that we have done a certain amount of work on it, and therefore some energy has been stored in the spring. So let's look at this. So we can look at this graphically, and if we apply a force on the spring, of course it will extend a little bit. We can plot this on a graph. So if we can imagine that this is the unextended length of the spring, this is the spring in its original length, tied to a rigid support, so this does not move. And when we apply the force, this spring will extend a little bit. We can measure the size of the force along the y-axis, and we can measure the distance that it's extended by, the extension, along the x-axis. So if I apply a particular force, then I will get a particular extension. The particular force that I applied would have been able to, say, extend the spring from its original size a little bit more, and so the force would have caused that particular extension. So from its original length, which was 0 on the extension axis, it would have extended to this position here, which translates to this extension here. So the application of that particular force F1 would have caused an extension x1. Now, if I increase F1 just a little bit, then the extension that will cause will also increase just that little bit. And I can keep doing this. So if I keep applying the force to increase it slightly, so we're going up there, then the extension that will cause will also increase slightly. And we can see where this is going, because this will lead us into, as I increase the size of the force, I increase the extension, and this will happen in proportion to the force until I have my maximum force that I can apply, so therefore the maximum extension. So if I keep increasing the size of the force, then I will keep increasing the extension that I have caused from the original length of the spring there, and so the extension will increase until the length of the spring increases too. This linear relationship between force and extension can be expressed as F equals a constant times the extension, and this is known as Hooke's law. Now, since work was done on the spring, there must have been energy stored in it. And the energy stored in the spring must equal to the force applied times the distance it was applied through. But in this case, the force that was applied was not constant, but was variable. It started from 0 and then increased gradually until reaching the maximum final value to cause a particular extension. So the work done must be equal to the average force that was applied. So if the average force, if we started with 0 and ended up with a force F, the average force was half of that. So the energy stored is equal to the average force, which is a half F, times the extension that that force finally caused, which was X. And since, of course, F is equal to Kx, we can replace F with Kx, and so we have the energy stored equals to a half of F, which has been replaced by Kx, times X, and so we get a half equals Kx squared. So we have three mathematical expressions there. One is the expression for Hooke's law. It says that the force is equal to a constant times the extension. That constant is known as the spring constant and has units of newtons divided by meters, newtons per meter. The energy stored in the stretched spring is equal to a half times the maximum force times the maximum extension. And another expression for the energy stored is a half times the particular spring constant times the extension squared. Now, you can appreciate that it's possible that the spring is very much stiffer, which means that we need a much larger force to cause the same extension, or very much less stiff. So a very, very small force will cause the same extension. And so the spring constant is actually a characteristic of the spring itself. And all materials that have a spring, that have some sort of springiness in them and can store energy when we apply forces to them, have a spring constant. They don't necessarily need to be springs. For example, an elastic band that can be stretched or compressed, of course. Springs can be either compressed or stretched. So the force F is the force of compression or stretching. Another way to look at it is that the work done is actually equal to the area under the force extension graph. So that area is actually found by a half of F times X. If that is the stretching force F, representing this side of the triangle, and that is the extension X, representing this side of the triangle, then to find the area of the triangle is the force F times the distance X. That gives us the area of the rectangle. So half of that is the area of the triangle. So in summary, when forces are applied to stretch springs, work is done and energy is stored in them. That energy can be then used to transfer to other uses. For example, in toy guns, we normally have springs that are compressed and perhaps little pellets put in them, and the release of that energy, which is equal to a half Fx, could transfer to kinetic energy of the pellet, of the ball, let's say, and if we were to fire it vertically upwards, perhaps from kinetic energy, then into gravitational potential energy.